Hello everyone, I would like to welcome you all for today's lecture. Before we continue with wherever we left last time, I would like to have a brief recap of the last lecture. What we discussed in the last lecture was the use of dimethyl dioxazine and some other dioxazines which are useful for the conversion of olefins to the corresponding epoxide. So, the first one and the most popular dioxazine is dimethyl dioxazine, whose structure is this, and I mentioned last time that one can take different ketones and one can prepare the corresponding dioxazines, particularly in situ, that means inside the reaction, and carry out the epoxidation of olefins. It becomes more useful if one has a reactive dioxazine somewhat like this, having an electron withdrawing group such as CF3, mainly because such dioxazines react with electron deficient olefins a bit faster. And of course, we can also take the chiral ketones and carry out the formation of the dimethyl dioxazines, and they can transfer the chirality to the olefins to prepare chiral epoxide. In this process I had mentioned a She catalyst and particularly from the D-fructose. So, if we have here this particular part attached to the fructose derived molecule, here is the ketone from the fructose, and if this part here is having oxygen as a acetonide protection, then the trans olefins can readily be epoxidized. We will discuss more later on about how are the other substituents that affect the cis olefins and the terminal olefins. So, this is what we did last time. Now, let us go further today with the utility of the dimethyl dioxazine or other dioxazines in organic chemistry. The use of oxone and a catalytic amount of a ketone is thus convenient. We discussed it last time also, and particularly if one wants to make use of it is in optically active preparation of the epoxides, then one can easily use it. If one wants to isolate DMDO or TFDO, that is trifluoromethyl dioxazine, if it is inconvenient, then of course you can do the in situ preparation. An example of this kind is here. Here for example you have a substrate of this kind, and if you have this enol ether, then one can prepare a very interesting way of making the corresponding dioxazine is to use this ketone which has a ammonium salt, so that it is soluble in water, and one can have the oxone and a potassium hydroxide buffer, and under these conditions the epoxide which is going to form from this double bond, that means this is the epoxide that is expected to form. If this is the other part of the molecule, then this can open up in this fashion particularly and form the corresponding hydroxy ketone, which is what is done in this case. So, as you can see that this double bond is highly electron rich. This double bond is electron rich, these two are electron deficient olefins, and this is highly aesthetically hindered. So, this such a molecule which has 4 different double bonds but then only one of them reacts, and since it forms an electron rich epoxide under the conditions, then it cleaves to the corresponding hydroxy ketone. What is the mechanism of the reaction that is taking place in by using this oxone to the corresponding epoxide? So, what happens is that it starts with the ketone, whichever ketone that you start with, it reacts with the oxone, that is mainly the monoperoxy potassium persulfate, and that reacts to form to the ketone this particular intermediate. Now, this intermediate is formed because of the attack of the peroxysulfate moiety, and now this under basic condition the OH minus takes up the proton from here to form this O minus, and that under intramolecular condition opens up to form the dioxazine here. Now, this dioxazine reacts with the olefin present forming the epoxide and regenerates the corresponding ketone, that is this type of ketone. So, we have started with the ketone, and then under the basic conditions it allows the intramolecular attack of O minus onto the oxygen, because you have this sulfate ion as a leaving group, and then it undergoes the corresponding formation of the dioxazine and of course epoxidation. One of the problems that is found, that if the condition is not much of basic, then there is a possibility of this bare vinegar oxidation to take place. So, you have a possibility of bare vinegar oxidation, that is because what you have is this path as a leaving group. So, if this path is as a leaving group, then there is a possibility that the R2 group or R1, one of the two groups, can migrate from here, and this can go forming an intermediate of this type, where you have a possibility of positive charge being formed. Now, this is what we see in the bare vinegar oxidation. We have 3 center, that is this one and this one, 3 center 2 electron, that is carbon R2 bond, and therefore we form this type of intermediate, and this is what eventually leads to the formation of this ester. So, this possibility can also occur if the condition is not properly maintained, but then there are ways to circumvent this. So, the reactions are conducted in buffer medium, often biphasic mixtures with phase transfer catalyst, which is what is PTC. Addition of potassium carbonate increases the rate of formation of DMDO, but also lowers oxone stability. It is found that the oxone under the basic conditions is somewhat less stable, but then if we add potassium carbonate, as we did it in the previous case here, the potassium carbonate allows the deprotonation of this hydrogen easily, and then this negative charge attacks onto this oxygen and forms the corresponding dioxazine. So, this can be increased by the addition of potassium carbonate or by increasing the basic medium. But then under the basic medium, the oxone stability is somewhat less. Obviously, it is very clear that the oxone's nucleophilicity is high because of the deprotonation of the proton under basic conditions, and that leads to higher reaction rate also. But then at the same time, higher pH disfavors the bare vinegar oxidation as the site reaction. As we discussed, we can go back to the last slide, that this bare vinegar oxidation occurs by the loss of the sulphate moiety. When the sulphate goes away, there is a migration of the carbon R2 bond to the oxygen, which will now be kind of electron deficient, because once the sulphate leaves or is about to leave, then you generate a delta positive on this particular oxygen, you have a delta positive to be formed, and then the carbon R2 bond goes there to form this intermediate. So, this is Baeyer-Williger oxidation, and then we want to avoid such a Baeyer-Williger oxidation. So, you can use basic condition. So, basic condition helps in decreasing the Baeyer-Williger oxidation, increasing the oxirane formation, but of course it allows a somewhat decomposition of the oxone. Hence, auto decomposition of oxone at high pH can be overridden if the ketone is sufficiently reactive. So, what can one do is the higher pH, as I said, higher pH disfavors a Baeyer-Williger oxidation as a side product formation. So, the catalyst remains active. So, basically you start with the ketone and make the oxirane dioxirane, but then you have to use basic conditions, and if we increase the reactivity of ketone, then the possibility of Baeyer-Williger oxidation is less. The nucleophilicity obviously of the oxirane, this oxone increases, and then the reaction becomes more or less like very sufficiently fast. So, reactivity of ketones can be increased by having an electron withdrawing group, and very clearly it leads more to the dioxirane, and thus Baeyer-Williger oxidation is reduced. As I discussed and introduced, we have a sheep oxidation. So, the one can start from D-fructose and prepare this particular ketone, which is what is used in the Shees epoxidation of converting an olefin to the corresponding epoxide, which is chiral, and there are references which I mentioned here. They are very important references. What is found is that instead of this acetonide here, if we increase and change the substituent here, say Y. So, if OY is this, which is what we have written here in this form, then this is useful for trans olefins. If we change the substituent there and make it like ON Bock here, this is found to be more useful for the cis olefins, and if we have this N toluene here, then of course it is useful for the terminal olefins. The mechanism and the transition states are somewhat complicated, so I would not like to discuss it here, but one can check these references and get to know how does this affect the corresponding olefins. Now, how do we make the She catalyst? It is very easy. You can take the D-fructose and you can put the acetone in the presence of say perchloric acid as an acid catalyst, and this diol, which is a cis diol, and this diol, which is relatively free away from the steric point and can easily react. So, both of them react to form the corresponding diacetonide, and then you can oxidize the hydroxy group using PCC, pyridinium chlorochromate, and we can prepare this particular ketone, which is what is reacted with oxone to form the corresponding dioxirane. On the other hand, if this gives certain type of chiral induction, then opposite of that can be expected to form from the L-fructose based ketone. If this is the L-fructose based ketone, as you can see that there is a exactly opposite of the D-fructose based ketone. These two are beta, where they were alpha here. In a similar fashion, this was alpha, so it is now beta, and this is beta, and here it was alpha. So, it is exactly opposite because D-fructose and L-fructose are actually mirror images of each other. So, whatever chirality is going to come of the epoxide, which is here, by using this ketone, it will be exactly opposite by using this ketone. So, there is a great advantage and it is very easy to prepare from D fructose and L fructose. Now, we go to the next topic, that is oxaziridines, and they are shown like this, the structure. So, we used dioxirane, but now we are going to use the oxaziridines. Now, what are those oxaziridines? They are exactly similar to the dioxirane, but then one of the oxygens is replaced by the nitrogen. Now, this leads to interesting possibilities, and it has been popularized by Franklin A. Davis, and it leads to a variety of different types of reactions. For example, it is useful in converting a ketone to the corresponding alpha hydroxy ketone. So, alpha hydroxylation is one of the reactions that is found to take place, and this is how it works very well. So, here this oxaziridine, as one can imagine, could be a source of nitrogen or could be a source of oxygen. So, these examples which are shown here illustrate that oxygen acts like an electrophile. So, alpha hydroxylation is one product. Olefin can react with the oxaziridine to form the corresponding epoxide. It can also oxidize a sulfide to sulfoxide by transfer of oxygen. So, these three examples are basically of oxygen transfer. Nitrogen can also be transferred if one takes amine, for example. So, you can start with an amine and you can make this hydrazine. We are transferring nitrogen. There are possibilities of transferring nitrogen similar to the epoxide type of formation. One can also get the corresponding aziridines. So, you can get this type of aziridine molecule, which is a nitrogen analog of epoxide. And just the way alpha hydroxylation was done, we can also use alpha amination and get the corresponding amino ketone, and this is basically because of the nitrogen transfer. So, these are the examples of nitrogen as an electrophile. How do we prepare these oxaziridines? There are several methods, but I have shown here two methods, that one can start with imine starting from the corresponding ketone. So, if we start with the R2 R3 ketone here, and we can prepare the corresponding imine easily, and we can then react it with any peracid. So, any peracid such as metachloroperbenzoic acid, peracetic acid, or any other peracid, we can easily epoxidize this imine to form the corresponding oxaziridine. Otherwise, one can take on this nitrogen some sort of leaving group. So, a molecule of this kind where X is chlorine or a kind of a leaving group like OSO3H, and of course, R1 can be hydrogen, methyl, or any other substrate, and or a group, and then it forms the corresponding oxaziridine. Initially, it was found that if the substituent on nitrogen is small, somewhat like this, you have a hydrogen or a methyl or acetyl, a small group, then nitrogen acts as an electrophile, because there is, unlike dioxirane, which is dimethyl dioxirane or any other dioxirane, here there are two different possibilities. One is oxygen as an electrophile, other is nitrogen as an electrophile. Therefore, one has to be a little bit careful. So, it is always possible that nitrogen can get transferred instead of oxygen, or oxygen get transferred instead of nitrogen. So, one has to be careful, and a lot of work has been done, and as I mentioned that if we have a small substituent on the nitrogen, then there is a possibility of nitrogen transfer. That is because if nitrogen has small substituent, then this bond can easily break and you can transfer the nitrogen. On the other hand, it was also found that if we have a group somewhat like this here, para-cyanophenyl for example, then it is possible with the group of like Bock group present on the nitrogen, you are making this particular nitrogen as more electrophilic nitrogen, and also there is a possibility that you can break this bond here, and the negative charge here will be stabilized because of the electron withdrawing cyano group attached to the para position of the phenyl ring. So, it was found that this can also act as a good source of nitrogen. So, there are examples in the literature where these two and somewhat similar have been utilized for the transfer of the nitrogen from oxaziridine. Now, just to tell you about what are the barriers for the nitrogen inversion. Obviously, we go from ground state to the transition state, inversion of the transition state, the strain will increase, and when you have an N-alkyl substituent versus N-acyl substituent, the strain increases when we have the alkyl group, and strain decreases when we have electron withdrawing group. So, inversion barrier basically decreases with the electron withdrawing groups, because the lone pair of electron on the nitrogen here would now be in conjugation with this. Therefore, there is an easy possibility of the inversion of the configuration here from the nitrogen. At the same time, inductive effect of the oxygen increases the S character of the lone pair of electrons on nitrogen and makes it more pyramidal. So, that is another property of these type of oxaziridines. So, basically it is just to illustrate or show that what kind of properties these oxaziridines can have. Now, as I already have discussed that they oxaziridines can transfer heteroatoms such as oxygen and nitrogen. They are easy to handle, that is one advantage, that they are very easy to handle, they are not unstable like dioxirane, like dimethyl dioxirane or something like that. Of course, they are reactive, but we have a possibility of having an electron withdrawing group on the nitrogen, thus making the reaction, the stability of the oxaziridines a bit more, and at the same time they are fairly reactive. Now, there are several ways by which one can make the oxaziridines with having a property of electron deficiency. For example, oxaziridinium salts or perfluorinated oxaziridines are sources of electrophilic oxygen. How? Now, for example, if one has an electron withdrawing group here, so and also an electron withdrawing group on the nitrogen, then there is a possibility of ready cleavage of this oxygen nitrogen bond to form this particular anion on the nitrogen, which is basically due to the influence of the electron withdrawing group on the nitrogen. At the same time, because R is also an electron withdrawing group, therefore there is a easy possibility of such cleavage, and that leads to the formation of the nucleophile reacting specifically with the oxygen, and the imine is regenerated. So, the regenerated imine can again be epoxidized and oxaziridine can form. At the same time, one can also take oxaziridine with an ammonium salt here, such as this. This is going to be also a source of oxygen here, electrophilic oxygen, because your nucleophile will preferentially attack onto the oxygen and cleave this oxygen nitrogen bond, and therefore we can get the same as above, that you have the transfer of oxygen to the nucleophile. So, there are ways of manipulating the conditions of this reagents to see if nitrogen is transferred or oxygen is transferred. Now, as already discussed earlier, that we have oxaziridines with small substituents on nitrogen act as nitrogen transfer, with bulky or electron withdrawing group on nitrogen act as oxygen transfer reagents. So, what are the oxygen transfer reagents? There are 4 of this kind I have already shown here: N-sulfonyl oxaziridines as it is shown here, then N-phosphenoyl oxaziridine, then you have oxaziridinium salts which are here, then you have perfluorinated oxaziridine. So, these are the 4 different types of molecules which can act for the transfer of oxygen on it to a nucleophile. Now, what are the order of reactivity for transferring such oxygen in comparison to say metachloroprobenzoic acid? And this is how it has been found that we have the perfluorinated oxaziridines react very fast, then you have the corresponding salt of this kind, oxaziridinium salts, then that is more than the metachloroprobenzoic acid, which then is more than the corresponding sulfonyl type of oxaziridine, and then phosphenoyl type of oxaziridines are less reactive than the corresponding sulfonyl type of oxaziridine. So, this is the reactivity pattern of the oxaziridines that one can think about it. Now, that depends upon the reactivity of the nucleophile that we have it. So, based on that, if we have a possibility of the order of reactivity of the nucleophiles, then one can match readily with the oxygen source as well as the enolate nucleophilicity and decide which combination one can take. Now, order of reactivity of olefins or the olefin type of substrates is as follows with respect to the N-sulfonyl oxaziridines. Normally N-sulfonyl oxaziridines are more often used, they are stable, easy to prepare, and therefore the reactivity has been very much studied with N-sulfonyl oxaziridines. And now you can see that the enolate ions can easily be prepared at low temperature such as -78 degrees, and these enolate ions can react with the N-sulfonyl oxaziridines very fast, because you have a clear negative charge and therefore the nucleophilicity of the double bond is very high. So, we use at -78 degrees, which is, that means at a very low temperature. Now, we have an enamine that also is very reactive, because now you have a lone pair of electron on the nitrogen that donates the electron density to the double bond. The reaction can be carried out at room temperature. So, it does not require very low temperature, but room temperature is good enough. On the other hand, if you have an enol silyl ether of this kind, and that requires room temperature to 60 degrees as temperature for the epoxidation to take place or reaction with oxaziridines to take place. If we have a normal olefin like this, then it takes around 60 to 70 degrees. That means this can react even at room temperature depending on the reactivity of enol silyl ether, but can be done up to 60 degrees temperature. But then you have less nucleophilic olefins such as simple olefin, then you need 60 to 70 degrees, and if we have electron withdrawing group on the double bond, then the molecule is somewhat unreactive. For the nitrogen transfer reagents of this type, what you need is an unsubstituted oxaziridine. So, we have somewhat like this, or you have an alkyl. So, you have an alkyl group here and you have this oxaziridine or N acyl. So, you have here somewhat like this. So, these are the oxaziridines which are generally used for the transfer of the nitrogen for a nucleophile. So, there are different ways by which one can choose the reaction conditions and also the substrates and also the oxaziridines, and accordingly one can carry out the reaction depending on what is required. Now, what are the reagents for the alpha hydroxylation of enolates to form chiral alpha hydroxy ketones? One of the reagents that has been used is oxodiperoxy molybdenum pyridine hexamethyl phosphoric triamide complex, which is shown here. This L is pyridine and L1 is HMPA, which is hexamethyl phosphoric triamide. So, these two are the ligands which are achiral, and therefore, this particular complex is an achiral complex. Now, this acts as an oxidizing agent, and if we react a chiral molecule like this, which is camphor, with a base like LDA and this MOOPH, this is what the reagent is, then under basic conditions like LDA, it would deprotonate the proton alpha to the carbonyl group, leading to this particular anion, which will exist as an enolate, and then there will be a nucleophilic reaction of this enolate from this carbon to the oxygen of this particular complex, allow to form this alpha hydroxylation. And since the beta side, that is the upper side or the exo side of the molecule, is sterically hindered because of these methyl groups, we get a mixture of two alpha hydroxy ketones in which the endo hydroxy group or the compound having endo hydroxy group is the major product. As you can see here, the endo-exo ratio is 5:1. Now, although the reagent is achiral, since the molecule, the starting molecule, the camphor is optically pure, so the product that we get is a chiral product. So, this is one of the ways by which we can get a chiral alpha hydroxy ketone. Now, in a similar fashion, if we take, instead of a ketone, if we take a cyano compound of this kind, in which there is no steric hindrance from the top side, that means the exo side is sterically unhindered, then if we do the deprotonation with LDA and react with the same molybdenum based oxidizing agent MOOPH, then once we get the anion of this type after the deprotonation alpha to the cyano group here, this can react with the reagent from the exo side, because the endo side in this particular case is sterically more hindered compared to the exo, and therefore we get this cyanohydrine in which the hydroxy group is exo oriented. So, this is one of the ways by which one can easily deprotonate a proton which is highly acidic. Under basic conditions, we can deprotonate that particular hydrogen and introduce a hydroxy group. So, we will stop at this stage today and take up the remaining parts of the oxaziridines such as chiral based reagents and the mechanisms and other aspects of it in the next class. So, please study whatever I have discussed today, and thank you, and we will see you next time. Thank you.